Diagonalization and unitary equivalent observables. The next question is how to find the eigenvalues and eigenkets of an operator B whose matrix elements in the old basis are assumed to be known. Right? So the matrix elements in the A representation is known, which means that we have got a matrix. We have a square matrix with elements given by A1, B, A1, okay, A1, B, A2, etc. Right? This is the matrix. This is the matrix representation of observable B or operator B in this basis, in the A basis. Okay. So this matrix is given. Suppose that this matrix is given. How do we find the eigenvalues and eigenkets? Right? Already you know how we find the eigenvalues and eigenkets if a matrix is given. Right? The same method works here. But anyway, we'll discuss this thing using the Dirac bracket notation, right? We'll discuss the same things that you're already familiar with. You know how to find the eigenvalues and eigenkets of a square matrix, right? Let's discuss these things using the Dirac bracket notation, all right? Now, the problem turns out to be equivalent to that of finding the unitary matrix that diagonalizes B. So what we are going to find is that in order to find the eigenvalues and eigenkets of this matrix, we just need to find the unitary matrix that diagonalizes this matrix. All right. So we look for a unitary transformation of this form. Let's say B prime is equal to U dagger BU. So we look for a unitary transformation of this form in such a way that the new matrix is diagonal. Right. And we know that if you have a diagonal matrix, the diagonal elements are the eigenvalues. So if you diagonalize a matrix, you immediately get the eigenvalues in this manner. Right? If you take a similarity transformation, if you find a similarity transformation that actually diagonalizes a matrix, then we know the eigenvalues. The eigenvalues are just the diagonal elements. All right? We'll see that the eigenkets or the eigenvectors are given by the columns of this transformation matrix. All right, we'll see that the eigenvectors or eigenkets are given by the columns of this unitary transformation matrix. Okay? This is what we are going to see now. We are interested in obtaining the eigenvalue B prime and the eigenket ket B prime with the property B acting on ket B prime gives B prime multiplied by ket B prime. Right? That is, when the operator acts on the eigenket, you get a number multiplied by the same eigenket. Okay? This is how we define an eigenvalue equation. Okay? Let's write this in matrix form. We see that this is a relation between two kets. This is a relation between two kets. And we know that kets are represented in a particular basis. Let's say that we are talking about the basis ket A prime, the set of eigenkets of observable A. All right. And we know that kets are represented by the coefficients or the expansion coefficients in this basis. We know how to find the expansion coefficient. So we can think of this as a ket, this as another ket. All right. So let's find the representation of this ket or the let's write this relation, this operator relation, as a ket relation, sorry, as a matrix relation, all right, as a relation between two column matrices. So we just take the components of this kets on both sides. Okay, so we'll see that the components will be related in this form. Right, so this B prime can be taken outside. Okay, so what is this? This is the corresponding column. This is the relation between two column matrices. This is the relation between two kets. Right, so this relation between two column matrices actually represents this relation between two kets in this particular basis. Okay. Now we can insert an identity operator here so that we can bring in a matrix. We can bring in the matrix elements of operator B or observable B. Okay, so I introduce an identity here. This becomes bra A double prime B ket A prime bra A prime, and then you sum over all A prime. Okay, and I've got ket B prime here. This is equal to B prime bra A double prime ket B prime. Here we have a square matrix multiplying a column matrix gives a number multiply the same column matrix. All right, a number multiplied by the same column matrix. Right, because this is the rule for a multiplication of a square matrix and a column matrix. Right, so this is basically the eigenvalue equation that you are familiar with from your matrix algebra. A square matrix acting on a column matrix or a square matrix multiplying a column matrix gives you a number multiplied by the same column matrix. Okay, This is the rule for multiplying a square matrix and a column matrix. There's a sum over A prime here. Okay. If you look at the eigenvalue equation, B acting on ket B prime is equal to B prime multiplied by ket B prime. This equation is for one of the eigenkets of B. Let's say this is for the nth eigenket. Okay, so we'll use this notation. We'll write B acting on ket BL, where BL is the nth eigenket. This is equal to BL multiplied by ket BL. Right. Now, if you look at the matrix representation of this equation in the A basis, we get a matrix equation here. Right, we get a matrix equation. Right, so we get one matrix equation actually for each eigenket. Right, so let's write it for the nth eigenket here. Let's write it for the nth eigenket. So this matrix multiplication or this matrix relation can be written as, this is actually a relation between two column matrices. Right, and this A prime actually labels the elements of this column matrix. Right, this A prime labels the elements of the column matrix. So this, let's take the nth eigenket, right, and let's look at the matrix representation of this in the A basis. So let's call these elements as bra A1, ket BL, etc. Right? And we'll denote this as CL. All right, this L stands for, says that this is for the nth eigenket, right, and this 1 says that it corresponds to the component along the A1 direction. Right, so like that you will see that there are n equations, one for each component of this. Right, for each ket A prime, for each of the ket A prime, or for ket A1 you will have an equation like this. For ket A2 you will have an equation like that. All right, so if there are n eigenkets, of the observable A, or if you are talking about an n-dimensional basis, then you will have n equations of this form. You will have n equations of this form, one for each eigenket of observable A. Right, now all these n equations can be written, we can combine it into this matrix equation. Right, so this will correspond to first equation in the n equations. All right, the first row multiplied by this column gives you BL multiplied by this number C1L. Right, similarly you'll see that this multiplied by the entire column gives you the second entry here, BL multiplied by C2L, etc. So all these entries together we can write it as a matrix equation like this, with matrix elements B11, B12, B13, B21, B22, B23. As we said, this is the row index and this is the column index. Right, this has only one index, it's a column matrix. Right, it has only one index, 1, 2, 3, etc. But we put an L here to say that these are the, what they say, these are the components of BL. These are the components of BL. Okay, so this equation can be written in matrix form like this. I hope this is clear. Right, and what are this B11, B12, B13, etc.? These are the matrix elements of B in the old basis or in the A basis. Okay, so these are given by Bij is equal to bra Ai B ket Aj, the matrix elements of B. Similarly, CKL, we said that this is the what is the component of the nth eigenket along the direction AK, ket AK. So this is given by bra AK ket BL. Right, so these are things that we are already familiar with. So what are we doing here? This is the representation of ket BL in the A basis. Right, what is this? This is the representation of observable B in the A basis. Right, and its elements are given like this. Okay, so we have got this matrix equation. Now this is a matrix equation which says that a square matrix acting on a column matrix gives you a number multiplied by the same column matrix, which is exactly the eigenvalue equation for matrices. You are familiar with eigenvalue equations of matrices. You might have seen equations of the form Ax equal to lambda x, and you have solved problems to find these eigenvalues and the eigenkets, correct? So we can use the same techniques here to find the eigenvalues and eigenkets of this observable. Right? Here, these indices I, j, and k run up to capital N, which is the dimensionality of the ket space. All right. Now, actually, we are back to good old matrix algebra. We have an equation of the form Ax is equal to lambda x, right? Where A is a square matrix, x is a column matrix, lambda is a number, and x is the same column matrix. All right. And we know how to solve this equation. This is known as an eigenvalue equation. We know how to solve this equation. right? We have already studied these things. So we can, so this equation, we see that there are non-trivial solutions for these eigenkets or eigenvectors, as we call it in matrix algebra. There are non-trivial solutions for this eigenvectors only if this condition is satisfied, a minus lambda I is equal to 0. Okay, so you construct this determinant equation, and this gives us an nth order equation in lambda. All right, we can solve that nth order equation in lambda to give us n different eigenvalues, n different possible eigenvalues. Okay, now we take each of that eigenvalue, substitute it back here, and find the corresponding eigenvector. Right, these exercises you might have done many times, finding the eigenvalues and eigenvectors of a square matrix. You have already done this. Okay, and we see that corresponding to each lambda, you substitute each lambda here and find the corresponding x. This does not determine x completely. It determines the eigen vector up to a multiplicative constant. All right, and if we impose more conditions like orthogonality or orthonormality, then we can completely fix the eigenvectors. All right, this is basic matrix algebra. Same thing is happening here. All right, we have an equation of the form a square matrix B, which is acting on a column matrix which we denote as CL, which gives you BL multiplied by CL. It is an eigenvalue equation for B. You solve, all right? So in order to find the eigenvalues, you demand that determinant of B minus lambda I is equal to 0. All right, you'll get an nth order equation for lambda. The n roots obtained are to be identified with the various BL we are trying to determine. So this is how we find the eigenvalues of the matrix B. What is this matrix B? This is the matrix representation of the operator B in the A basis or in the A diagonal basis. All right. So the matrix that we are talking about here is the matrix representation of operator B in this basis, right? In the A basis. All right. So if we are given this matrix, we know how to find the eigenvalues. We already know how to find the eigenvalues. Okay. Now, knowing the eigenvalues, knowing each eigenvalue, we can solve for the corresponding CKL. These are the elements of the eigenkets. Okay, up to an overall constant to be determined from the normalization condition. Right. So we'll get it up to an overall constant. And you can fix this constant by demanding that these are normalized to 1. We just demand that these eigenkets are normalized to 1 as we always want. Just demand that, sorry, b prime, b prime. We demand that this is equal to 1. That will fix, that will give you another one more condition that allows us to fix this constant. So we can determine these eigenvalues and the normalized eigenkets using the usual rules for matrix algebra. Okay. Now let's look at this CKL, the eigenkets that we determined. Right? These were given by AK, I think we wrote it like this, AK, BL. All right. But these things, this bar AK, ket BL, are nothing but the elements of the unitary matrix. All right. If you don't remember this, just check our previous class. Right. The CKL given like this are the elements of the unitary matrix involved in the change of basis. Right. So these are the elements of the unitary transformation matrix that takes us from the basis ket A prime to the basis ket B prime. All right. But if you go to ket B prime, all right, if you go to ket B prime, then the matrix B is diagonal. The matrix B is diagonal. If I go to ket B prime, the matrix B is diagonal. All right. So this is the reason why we said earlier that if we find the unitary transformation that diagonalizes B, so we have got a B which is not diagonal, just find a unitary transformation that diagonalizes B, it's equivalent to finding the eigenvalues and eigenkets. All right, eigenvalues are just the diagonal elements, and the eigenkets, what are the eigenkets? All right, so this actually means that the CKL, right, if this CKL, what are the CKL? These are actually the elements of each of the eigenket, right? The matrix elements of, so sorry, I think we should say it like this. These are the expansion coefficients for each of the BL in the basis A, in the basis A. Okay. What does this mean? This means that our unitary, the unitary matrix, unitary transformation matrix that diagonalizes B, right, or that takes us from ket A prime to ket B prime is just constructed out of the eigenkets, right? So we found that, so we could go both ways. If we know this unitary transformation matrix, then we know the eigenvalues and eigenkets, all right? Or if you know the eigenvalues and eigenkets, or if you know the eigenkets basically, or the column matrices that represent the eigenkets in a particular basis, you just arrange them in a square matrix, right? You write down the first eigenket here, the column matrix that represents the eigenket here, the second eigenket here, the third eigenket here, etc. Right? You write all these eigenkets together, and then you will get the unitary transformation that diagonalizes B. Right? I hope this idea is clear. I think you might have seen similar things when you were talking about similarity transformations, etc. Right? Similarity transformations that diagonalize a matrix. I think you might have seen, you might have learned how to construct these things. All right? So here we can construct the unitary transformation or the unitary operator that diagonalizes B by simply arranging the eigenkets of B. So when I say eigenkets of B, I actually mean the column matrices that represents the eigenket, right? The column matrices that represent these eigenkets, okay? The column matrices that represents these eigenkets in the A basis, all right? So finding the eigenvalues and eigenkets is equivalent to finding the unitary transformation that diagonalizes B. Okay. All right. Now, for this procedure to work, the hermiticity of B is important. All right. So you should remember that this works only for observables which are, or operators which are Hermitian. For example, we can consider S plus. It's a non-Hermitian operator, and the corresponding matrix in the SZ basis. Okay, I think we have written down this matrix, and this matrix, all right, it cannot be diagonalized by any unitary matrix. All right, you cannot diagonalize this matrix by a unitary matrix. Right. So this technique that we discussed before works only for Hermitian matrices. Okay. Let's conclude the section by discussing a remarkable theorem on the unitary transform of an observable. Now let's consider again two sets of orthonormal bases. One is constructed out of the eigenkets of observable A. The other one is constructed out of the eigenkets of observable B. Right? So this we call as the A basis and this the B basis. Now we know that if we have two different sets of bases, we can connect the kets in this basis sets by the unitary operator defined as U is equal to sum over K, ket Pk bra Ak. Right? So so this means that I can take every eigenket in this set, right, and go to a corresponding ket in this set by the action of this unitary operator. Right? I think we have seen this. Now, knowing U, we may construct a unitary transform of A, right? Unitary transform of operator A, which is given by UAU inverse. Right? Then A and UAU inverse are said to be unitary equivalent observables. All right? So when we say these are unitary equivalent, what we mean is that they have the same eigenvalue spectrum as we are going to see. All right. Now remember, this is not the same as the transformation of the matrix that we discussed earlier. We are talking about, here we have got a transformation of the ket. So this transformation takes you from one ket space to another. Right. We can construct a transform of an operator A, which is given as UAU inverse. Right. This is a transformation. This is a transformation of the operator itself. Right. Then we say that UAU inverse and A are unitary equivalent observables. Let's see what this means. We start with the eigenvalue equation for A. A acting on ket AL is equal to AL multiplied by ket AL. Let's apply a unitary transformation to this, all right? The unitary transformation that we just defined. So let's apply this unitary transformation. U A acting on ket AL is equal to, you get, since it's a number, I can write it here, and then U acting on ket AL. Okay. Now this is in a nice form because U acting on ket AL will give you ket BL, right? But here in between this U and this ket AL, there is this observable A, right? So in order to write it in terms of ket BL, let's write a U inverse U here. Okay, there's nothing wrong with writing a U inverse U here because U inverse U is the identity operator. Then this becomes UA U inverse, and then U acting on AL is equal to AL U get AL. Alright. So we actually see that this is already in the form of an eigenvalue equation. Right? We have got some operator acting on some vector or some ket. You get a number multiplied by the same ket. This is also if this is an eigenvalue equation, then this is also an eigenvalue equation, but the eigenvalue is the same, right? It's more instructive if you write it like this because U acting on ket AL is ket BL by definition, right? So we get UAU inverse acting on ket BL is equal to the same eigenvalue AL multiplied by ket AL. Right? So we see that the operator A and operator UAU inverse have exactly the same eigenvalue AL. They have the same eigenvalue AL. Alright. Now, since these operators have same eigenvalue, we call them as unitary equivalent. The operator A and the operator UAU inverse have the same eigenvalue. They are called unitary equivalent operators or unitary equivalent observables. Now it tells us that ket B prime are the eigenkets of UAU inverse with exactly the same eigenvalues as the A eigenvalues. In other words, unitary equivalent observables have identical spectra. The eigenvalue spectrum of unitary equivalent observables are identical. Right? They have the same eigenvalues, the same set of eigenvalues. The eigenket BL, right? By definition, these are the eigenkets of operator B. So this eigenket BL actually satisfies the relation B acting on ket BL is equal to BL multiplied by ket BL. Alright. So this BL are already, so what we have here is UAU inverse acting on ket BL is equal to AL acting on ket AL multiplied by ket BL. Right? This is what we have. Right? But these ket BLs, which we found are or eigenkets of UAU inverse, we have found that this ket BL are eigenkets of UAU inverse with eigenvalue AL. Right? But we have defined these kets BL as the eigenkets of operator B, which satisfies the eigenvalue equation. B acting on ket BL is equal to BL multiplied by ket BL. Alright. So what does this mean? This means that this eigenket BL, this eigenket BL is a simultaneous eigenket of both B and UAU inverse. Right? The operator acting on UAU inverse, the operator UAU inverse acting on ket BL gives you a number multiplied by ket BL. Okay. The operator B acting on ket BL also gives you a number multiplied by ket BL. Right? This means that ket BL is a simultaneous eigenket of both UAU inverse and operator B. Right? In other words, B and UAU inverse are simultaneously diagonalizable. They can be simultaneously diagonalized. Okay. Now, in cases of physical interest, we'll see that UAU inverse is the same as B in most physical cases. All right, most cases of physical interest, we'll see that UAU inverse is actually B. All right, we'll look at an example. As an example, let's consider Sx and Sz. Right? Now later we'll see that they are related by a unitary operator, which is actually a rotation operator around the y-axis by an angle pi by 2. Okay, so if you take Sz and this operator Sz and subject it to a rotation around the y-axis by an angle pi by 2, you will get Sx. Right? So there is a unitary transformation that connects Sz and Sx. So we can write Sx. All right, from this information, we have not yet discussed these things, but we can actually show that Sx has the form USZU inverse if this USZU inverse corresponds to a rotation about the y-axis by an angle pi by 2. All right. Now we now know that, so we can say that Sx and Sz are unitary equivalent observables. These are unitary equivalent observables. Okay. Now our theorem says that unitary equivalent observables have the same eigenvalue spectrum. This also we know because Sz has eigenvalues h bar by 2 and minus h bar by 2. Sx also has eigenvalues plus h bar by 2 and minus h bar divided by 2. Okay, so we know that Sx and Sz exhibit the same set of eigenvalues, namely plus h bar by 2 and minus h bar by 2. All right. So we see an example where our theorem actually holds. Right. So this is an example for unitary equivalent observables having the same set of eigenvalues. All right. So I think with that theorem, we can conclude our discussion of transformations, all right, going from one basis to another. Right? Thank you.